So as you can see, it's tapping in now. And I'm going to switch my screen also to make sure that this is good. I'm going to mute it because I know I will have feedback if I don't. So as you guys can see now, it's up. Okay, it is up. So I'm going to go ahead and switch my screen so that I can have access to that as well. Okay, well, thank you so much for the update, Serenity. I appreciate that. Okay, guys. Okay. So I believe we're good to go now. So are you guys ready? I'm ready. Let's go ahead and get into our lesson today. So for the past week or so, a couple of weeks now, we've been doing a lot of chemistry tutorials. And I know a lot of times when we're doing these chemistry tutorials, some students want access back. Well, here you got it. So for those of you all that are hopping in and logging in now, you will have access to that platform on my YouTube channel. So if you all are ready to go through that, you can go on my YouTube channel also to come back to this video, and it's Learn Chemistry with Professor TK the Chemist. Okay, Learn Chemistry with Professor TK the Chemist. Now, what I would also like to say is that as you guys come in, tap the screen to continuously show the algorithm that we're in the building, giving out great lessons, chemistry lessons each week and each day. Sometimes my schedule will be off a little bit, but if it is, you can always DM me if you need further help. I have misplaced my my phone holder, so I'm gonna be over here remixing my stands and everything so that I can make sure that it does not move. Okay. So I appreciate all of you guys for coming in the building. Hey Lulu, hey Chavez, hey Princess Star, hey Sweet Turkey Barbecue. I hope all of you guys are having a great day on Tuesday. My day is okay. You know, I'm gonna get through it. You know, it's all good. Okay. But what I wanted to show you all today is something that deals with molecular drugs. Okay. And you're probably wondering, like, what? Wait, what's she talking about? Molecular drugs? What's that? So let me kind of introduce a couple of things to you. Okay. I'm going to give you all some background. Now, many of you guys may watch Breaking Bad, and every time we talk about Breaking Bad or we bring up chemistry and what you could do with chemistry, so many students ask, well, can you make drugs? And I'm like, well, I'll just say this. I can give you the chemical formula for what you see, and we can talk about it that way. But as far as mixing things, no, we're not about that life. Okay. However, I do know in chemistry labs, like organic chemistry or even a general chemistry 2 class, you'll typically be able to synthesize aspirin. You'll be able to make aspirin with salicylic acid. But when you talk about molecular geometry of drugs and what that means in the real world, let me go ahead and break it down for you. So anytime you're taking certain drugs, let's say that you are taking aspirin. Okay, we'll go with aspirin. Well, the only time it typically will dissolve in your body is if you have something like water that's going to help it move through your system. Certain drugs are water soluble drugs, and then other drugs are fat soluble. Also, some of your vitamins. Sometimes when you see vitamins and you're taking vitamins for whether it's a certain condition that you have, or you're just trying to remain healthy because you don't get it in your food, there are certain vitamins that can actually stay in your body long term. And then there are some that we say you can basically urinate them out, okay, or excrete them out. Things like vitamin C goes through your system really quickly. And some people say, you know, some of these vitamins are just more or less expensive pee. It's like expensive pee because it comes out so quick. But on the other hand, you may have fat soluble drugs, which means it'll actually connect or accumulate in the fatty tissues of your body, and then it will linger and stay in your system a lot longer. One of the examples I can think of is like vitamin D, or even fish oils or cod liver oil. Certain drugs and even marijuana, for those that partake in recreational drugs like that, marijuana stays in your system for a very long time. Now, a couple of months ago, we did talk about, yes, Dr. Sheldon, yes, of the Big Bang. We did talk about a long time ago half-lives of drugs. Well, now we can get into the shapes of those molecular drugs to see why so many people can't beat drug cases in the court of law. So when you have drugs like marijuana and things of that nature that lingers in your system, there are some biases with that from a medical standpoint, from a biological standpoint. So again, if you are taking certain drugs, okay, some of those drugs will linger in your system if they are fat soluble. So as an example, as I mentioned to you before, there are some vitamins that because they are fat soluble, they can also build up a toxicity within your system. And this is why you want to be very careful when it comes to things of that sort. Okay, you've got to be very, very careful. So here's one of the most popular drugs here. I'm going to zoom in so you all can see this, okay? And some other background too, real quick, as I'm zooming in. You may have heard this phrase, likes dissolve likes. So like if we like each other, if we get along, if we're in the same category of friendships or we have the similarities, it's like iron sharpening iron, okay? Nonpolar will typically dissolve other nonpolar substances. Polar compounds will dissolve other compound substances, okay? So if you think about drugs and their ability to be polar, this means that it will be soluble in water and can be taken orally or injected into the system. Okay. So again, if you think about certain drugs that you can take by mouth, they'll dissolve when you drink it with water. That's right, number 19. Like polar dissolves with polar. That is correct. So here's another example. If you have fatty soluble drugs, though, they have to be oftentimes given to you intravenously, with a needle in order for it to go straight to that part of the body and to get to your bloodstream a lot quicker. So certain things can be given orally or they can be given intravenously. Okay. Now you've got these two drug molecules on the screen, and I'm going to explain what they are. But here's how we get into this in chemistry when we talk about stereoisomers. Okay. Stereoisomers. And I'll give you the definition of that in a second. But before I do, let me zoom in so y'all can see this. Okay. Now, if you take a look, you've got what's called L-methamphetamines and D-methamphetamines, okay? D and L. Can you determine the difference between them? Do they appear to be the same thing? Look at the way they are, and I want you to tell me L-methamphetamines versus D-methamphetamines, which one do you think is going to get you some serious time in jail if you're caught with them? Which one? And then the next question, which one do you think is the legal one? But before you answer if you're going to say which one is legal, just put your answer for legal or illegal, okay? So if you say L is legal, put L legal. If you say L is illegal, put L illegal. If you think D is legal, put D legal or D illegal. Whichever one you want to answer by, say that, and we're going to see if your answer is right. But looking at them, they do look the same. However, one is L and the other one is D. They're like mirroring each other. Like if you're looking at my computer screen, it looks like you can see this straightforward. If I had writing on my shirt and I flip the camera to myself, my writing may look backwards to you. Okay, let's see. Cha said, are they moving different directions? No, they'll move the same way. So like if I take this and move it this way, if I take this and just twist it around, okay, matter of fact, let me show you better than I can tell you. I'm gonna see if I can switch this around, okay? Let me move this out the way. Okay, so if I were to reposition this picture, I'm gonna rotate it. I rotated it 90 degrees. I'm gonna rotate it again. And as I just keep rotating it, okay, I flipped it upside down. I flipped it horizontally. Does that change anything? No, we were discussing stoichiometry, but we don't stay on the same topic, forever, ever. Okay. Yeah, so we're on geometry now, but no, this is not OChem for sure. Well, I would say it is somewhat OChem, but I'm actually going to get into how we actually draw these these molecules out. Here's the thing. Both of these appear to be the same, but if you are caught with L, guess what? You're good to go because L methamphetamines is nothing more than the meth that's found in Vicks Vapor Rub. However, D-methamphetamines is the one that will get you some serious time in jail. And this is the one that's often found in cold medications. In some locations, in some pharmacies, they make you sign and show your license if you want to get oftentimes Sudafed, because Sudafed has the one key ingredient that most people who make meth use. They call it shake and bake, where they put so many different chemicals in a bottle and they shake it and they're able to isolate the meth from that through a very I would say street-based format of chemistry. And as a result, you have them getting that one compound that people are looking for to get high on. Now, the reason why this is a problem is because in some court cases, they weren't able to determine the difference between the two. And they would have to hire a chemist to come in and discuss this. So now here's the definition of isomers, and then we're going to actually get into drawing this out. So an isomer, a stereoisomer, that is when two compounds share the same chemical formula and the same connections between atoms, but they exhibit differences in the way their atoms are arranged three-dimensionally. Now, no, I'm not a pharmacist. I am a chemist. I'm a chemistry professor. Dev guy, thanks for the compliment, I think. But here's the problem, though, with D-methamphetamines, because that's the illegal version, there are people who go around and do what's called smurfing, where they go from pharmacy to pharmacy trying to get as many packs of Sudafed as they can. But then some of the pharmacies are connected with each other, like in your small towns, and they're able to kind of catch you and say, yo, this person was just in here and they got 2 packs of Sudafed. And they keep it locked up behind the counter because of this reason. Now, here's the other problem too. Vicks Vapor Rub, while you say, okay, this should not be a problem because they do have the L-methamphetamines in the Vicks Vapor Rub, there are issues where, unfortunately, there was a case here in our area years ago where this young lady was a track star. She was rubbing icy hot on her body. And it can have the cool version or the hot version. But it also had meth in it as well, like because of the Vicks Vapor Rub. And as the methyl that was in it caused her body to overheat and caused her untimely death because she was using it to get rid of some of the aches and pains, as a track star. She was only in high school. So even though you're putting Vicks Vapor Rub on your skin, remember your skin is the largest organ of the body, of the human body, and anything that you're putting on your skin can do a lot of damage long term. And again, it depends on the amount. Now, all of this background is important because when we get into drawing out these structures, let me show you something else as another example so that you guys can see how this image actually looks from a different standpoint, okay? So, let me see, I think I downloaded the picture, and if I didn't, we'll just have to get that later. But no, I did not. But one thing I can tell you, though, is that when you look at these two drugs, or these two drug compounds, they can do a lot of damage. Now, how does this affect you guys in chemistry? Well, when it comes to drawing them out, this lesson deals with what's called molecular geometry, where you have to determine the shapes of them. But the first thing you have to do, of course, is use your periodic table. So let me go ahead and switch my page so that you guys can see that, okay? So here's an example of a periodic table of a chart that you would have to be privy to in order to do these problems, okay? So on your periodic table, there are so many different groups on here that gives you background information, okay? And as I've mentioned to you all before, group one, all the elements in group one have one. Hey, Scott, how you doing? Hey, Steve. Group one has one valence electron. Group two has two. We skip groups 3 through 12. When you get over here to groups 13 through 18, and let me zoom out a little bit so you guys can see it. When you get to groups 13 through 18, this is where they have to drop the one, and you just say for group 13, they have 3 valence electrons. 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18 has 8, which is a full shell. Thank you so much, Umbra. I appreciate that. I appreciate your kind words. So when you look at the valence electrons, okay, this tells you how many of those little dots you put around it. And the reason why this is important, if you're going into the healthcare field, this kind of makes sense for you if you're talking about giving a patient certain drugs and you wonder why you can't take certain drugs with other drugs because one will counteract the other. It's all based on this whole topic here of molecular geometry. It's all based on this topic. But for those of you all that are not pursuing the field of healthcare and you're just taking chemistry, that's one example I can tell you. Like if you're taking certain drugs, for your body, you wonder why you can't take certain blood pressure medications with grapefruit juice. Okay. If you're taking birth control pills, and then let's say you take an antibiotic, you will be having a baby knock on your door 9 months later because of that. Okay, because the antibiotic counteracts birth control pills, unfortunately. Okay, so let me go ahead and show you guys another example, or let's get into actually drawing this out. Okay, so here's an example here, and I'm going to give you the basic one. Okay, if I tell you that I want you to draw out the molecular shape for water, H2O, one of the first things you have to do is take out the hydrogen and take off the oxygen, and you're going to separate them. Right here, I've got 2 hydrogens in my formula. I have 1 oxygen in my formula. I'm going to look at my periodic table, and I know that hydrogen is in group 1, therefore it's going to provide 1 valence electron. So you multiply 2 times 1 to give you 2 valence electrons for hydrogen. Oxygen, you only have 1 of them. Oxygen is in group 16, but you're going to drop the 1 and you're going to say you have 6 valence electrons. So 1 times 6 is 6. But you add these 2 together, 2 plus 6 gives you 8 valence electrons. That is your total. Hello, LYN. I do not teach organic chemistry. I'm sorry, I don't. Now, when you get to filling this out, though, remember how I told you that hydrogen was in group 1, and it's going to provide 1 valence electron, right? And there are 2 of them. What I'm showing you now is what we call bookkeeping. I'm just showing you what each of your hydrogens are going to contribute, and you just cancel them out as you're working with them. Now, we do have 6 valence electrons for that 1 oxygen atom, so I'm going to put 6 around it. And you will always do either an individual or a pair. So I'm doing 2, 4, and 6. Now, background information with this. Elements that are in groups 14 through 18 must have 8 around it. The farther right you go on your periodic table, the more electronegative that element is, and that also means that element must go in the middle. Hydrogen will never ever appear in the middle, FYI. So those elements that are negatively charged typically go in the middle. Now, I'm going to draw this out, and I'm going to show you all how this is going to be drawn in terms of the molecular geometry. Oxygen is coming in with 6. So that's 2, 4, 6. I'm going to cross that out because we're done with that one. Hydrogen is coming in with 1, and it's going to go right there underneath that oxygen atom. Cross that one out. The next hydrogen is coming in also with the 1 that it's going to contribute. We're going to cross that out. And so now what you see here is that oxygen, the element that's in the middle, will be surrounded by 8 valence electrons. Okay? 8 valence electrons. Now, we're not done in terms of completing this picture. What we have to do in this particular case, we have to do what's called redrawing those dots, those pairs. And we're going to replace those pairs of dots or valence electrons with a dash. So this image here that you guys see will be redrawn. So let me take this one out so I can have some space here. Okay. And I'm going to go ahead and redraw that out so you all can see. So this structure here will become H, and those dots that we have here, a pair is equal to a dash. 2 pair, that's when you get into a double bond, and 3 pair is when you have a triple bond. Okay, just FYI. But again, we'll get into that later. I'm going to put my oxygen in the middle with the 2 on the top and the 2 on the bottom. And then I'm going to draw the other hydrogen. And there you have it. Okay? That's your picture for water, H2O. And I know this hydrogen looks like it's so far apart, so let me get a little bit closer so y'all can see. Okay? And that's it. And you just count to make sure that the total number of valence electrons that we started off with equals to the number that you see totally on your image. If I count these here, that's 2, 4, 6, 8. And if I go back to my picture, or excuse me, my math part, okay, up here, we have 8 as well, okay? You know we're going to do some more, right? Tomorrow, I will show you guys how to determine the shape, okay? So today, we're just drawing them out, but tomorrow, I will show you guys how to determine the shapes of these. Oops. Okay, so now, let's do another one, okay? Let's do another one. We're going to do sodium chloride, NaCl, okay? NaCl. You've got 1 sodium and you've got 1 chlorine. Good old table salt. You have 1 of each. Sodium is in group 1, so that's why we put 1 valence electrons. Oh, thank you. Thank you. So you've got 1 valence electrons here. For chlorine, we have 7. Okay, because remember, chlorine is in group 7. So, or it's group 17, but remember how I said you drop the 1 off, and that's where the 7 comes from. So 1 times 7 is 7. So 1 plus 7, remember, you got to add those together, and you end up with 8. Now, what are we going to do? Let's do the bookkeeping. You don't have to do this step. This is optional, but it just gives you an idea of how to know what you're working with from the very beginning. Remember, chlorine comes in with 7, and that's why I drew 7 dots around them. Again, you're going to either do 1 individual or a pair, but you never do like 3 side by side, okay? Like this would be wrong. If I put that little extra dot right there, that's wrong. So you never put them as 3. They either come solo or as a pair, okay? The only time you put 3 like side by side like this is if it was a triple bond, okay? Just FYI. But again, we'll get into those later, okay? Now, you've got 7 around chlorine, 1 for sodium. Remember, any element, okay, that's in groups, and I'm going to write this on the screen so you all can see. Groups 14 through 18 must have 8 around them. And if you have to share the pairs of electrons, then by all means do. But the elements that are in groups 14 through 18 must have 8, and they typically will be in the middle. But now, when you just have two elements, like this example, NaCl, all you're going to do is just draw the picture out side by side. Okay, that's all. So let me show you. Okay, so right here, we're going to start off with sodium. Okay, sodium with one little valence electron, because that's what it was contributing. Chlorine is going to come in and say, well, guess what? I only have 7 to donate to this particular bond, but I need one more from chlorine to give me a full octet rule of 8. So that's 1, 2, 3, 4, 5, 6, 7. Now I drew this with 7 blue dots so you could see that there were 7 right here that was coming from the original ion. And I also gave one to the chlorine from sodium to give it a full complete number. Again, this element here has 8, and it's called sharing, okay? That's where you get the sharing from. So all I'm going to do now is just simply redraw this, okay, with the dash, put chlorine here on the outside, followed by those extra pairs of valence electrons. Okay? Any questions so far from anyone? Any questions? And this is it right here for sodium chloride. That's how the picture looks, okay? And although we call these, the ones that are not attached to anything, like this one here, the ones I'm highlighting, those are called non-bonding pairs of valence electrons. Non-bonding pairs of valence electrons. They're not bonded to anything, but they do play a role in your pictures and in their shapes, okay? In their shapes. Now, we're going to do another one because I want to make sure that you guys are good to go. Okay. So you've got this next example here, NH3. NH3. We've got nitrogen. We also have hydrogen. We've got 1 nitrogen, but we have 3 hydrogens. Nitrogen is in group 15, but we dropped the 1, and that's where the 5 comes from. So we have 5 valence electrons. Hydrogen is in group 1, so that's where the 1 comes from, but we have 3 of them. So you have 3 valence electrons. And you add them together and you get 8. Again, the bookkeeping part is to go ahead and draw out what your picture should probably look like or represent, so that you can just, X them out or mark them off as you do your image. So now we're going to draw this picture and put it together so we know what we have. Okay, so over here, nitrogen is going to start off with 5. And I've got 2, 4, and 5. Now, remember, here's another little trick. Nitrogen has 5, right? What is the charge on nitrogen? If I were to ask you that question as a homework question or as an in-class question, and if you had access to the periodic table, you would tell me nitrogen has a charge of -3. And guess what? That's the number, that's the number of extra electrons that it needs in order to fill this element. See, chemistry is not difficult, but you've got to put 1 and 2 together to get the idea of what you're working with. Sometimes it's not always seen, but if you know patterns, it's so easy to give the answers. So here comes hydrogen now with the one that it was going to donate. Here comes the next hydrogen with the one it was going to donate. And then here comes the last hydrogen plus the one it's donating. And if you count the number of blue dots you see, each of those blue dots comes from what? Each of these hydrogens over here, okay? So hydrogen 1 right here, we're going to get rid of that one. See, right here. Hydrogen 2, get rid of that dot. Hydrogen 3, get rid of that dot. And if you count the number of blue dots you see, you can tell that they come from each of these hydrogens. And if you count the red dots, you'll notice that that comes from your nitrogen. Okay? And again, all we have to do is put this together. Okay? So I'm going to erase this so I can give us some more space. And I'm just going to redraw this out. And redrawing it means I'm going to replace those dots that forms a bond and put the extra 2 here over the nitrogen. And if you add your dots or even your dashes, they'll equal to 8. And that's it. That's it.